Welcome to another video. This is the first episode of a new series. It's not a build series, surprisingly, it's a theoretical series. As you can see from the title and on this paper, it says power system design, and to me it's the most interesting field in electronics, and it's a very important field. So far all of my questions, or most of the questions, have been regarding a power system. For example, people asking me how to drive certain motors, or how to make power converters or switch MOSFETs, converter topologies and such. One disclaimer before we begin: I'm not some sort of electrical engineer or something. Most of what I'm going to talk about is my own research, and I'm speaking from experience for things that have been working for me, and so far everything has worked out pretty well. The first episode of this series is going to be about power switches, or MOSFETs especially. I could also do IGBTs, but I don't have IGBTs yet, or use them as much as I used MOSFETs, and MOSFETs are mostly wider used in power systems, for example converters or motor drivers. Well, motor drivers actually use IGBTs, but you can as well use MOSFETs. So what you see here in front of me, they all have a common function. One specifically common function, which is switching. For example, this is a mechanical switch. You feed into a input variable, which is mechanical, in this example my hand, and you turn a electrical current on and off. Same here. Also here, relays, same thing, except their input variable is a signal. But most people, they get confused when you talk about transistors or MOSFETs, IGBTs, which is pretty weird because it's all actually the same. For example, here we have a MOSFET. We take a signal, a input variable, we have an in and an out. So if I can draw that for you, I'm going to make a drawing of this simple switch. It simply is a machine, and it has some in and out, but also there is a signal, which is, in this case, when I press the button, that is the signal. Same goes for here. Signal and in and out, which is basically the same thing. Also this relay, you just put a signal in, which then switches from in, and it turns it on, and it has an out. However, with switches you can just press it, but of course it's a mechanical device, therefore it has a speed, a maximum speed, it has efficiency losses such as that, and you can't really switch this 100,000 times per second as you can do with this. What I have in front of me this is mechanical, electromechanical. Then we have SCRs, which are diodes, which also take a signal in and then allows current to flow. Transistors, BJTs, and the MOSFET, of course. As I said, this is very easy to do, but there are some snakes with the MOSFET. And in this video we are going to discuss what some of the issues are with MOSFETs and BJTs and such. And we are not going to talk about these kind of units because they are not really used in high frequency power converters, for example, and SCRs mostly not as well, but they are handy to have because there are some issues with MOSFETs in general, and mainly that's due to high side and low side, which can become complex in nature. But we are not going to use diodes to switch our transformer, for example. And the BJT, well, the MOSFET is basically a bigger version of the BJT, but there are some slight changes. For example, that the gate is isolated, but we will talk about that later. So now we have a couple of MOSFETs over here. This is a P-channel MOSFET and this is N-channel. These three are all N-channel and this is P-channel. The difference we are going to talk about later, but for now we are going to stick with the N-channel. So let me draw a symbol of the N-channel MOSFET. So this is the basic symbol of an N-channel MOSFET, as you see right here. But this is not really accurate. This is due to different parameters that come with the internal workings of the MOSFET, substrate layout and such. But we are not going to talk about that. We are just going to talk about how to use them and how to use them efficiently. So you probably know this, but there's one thing you also have to remember, that most of these have an internal body diode. This is very convenient in most cases. For example, when driving motors or transformers, any inductive load will have flyback, which can escape from this route and complete this little internal circuit. But there's also many more applications for this diode. Well, the main pinouts for MOSFET is the D, the S, and the G. The D stands for drain, the S stands for source, and the G stands for gate. Now, even this is not all, and this is where most people will fail to see what's going on, because it's not very common to notice it, because it's in no data sheet as symbol, but it's there, and we will take a look at that a little bit later. But there is capacitance between all the pins. And then you get this circuit, which is a lot more complex than what we originally had. This capacitance is CDS, which is drain to source. As you can see, drain to source capacitance. This is the capacitance from gate to source. Simply said, just gate connects to here. If I can draw it. And this is capacitance gate drain. Now, while these capacitance must be kept in mind, we are going to take a look at that a little bit later. For now, we are going to inspect the data sheet and see what we can learn from it. For now, we are going to look at this one, the IRL Z44N. Now you will have to excuse me for using paint, but it's easy to use. So now we're going to take a look at the data sheet, or the first page of the data sheet of the IRL Z44N. Now, what is the first thing we see? We see the company name over here. We see the symbol, and here you can see the diode, which is included. We see the rated voltage. We see RDS on. Take a look at it later. And we see the rated current. D stands for drain. DS is drain to source. On the left hand side we can see logic level gate drive. What that means is logic levels are just one. If we draw the PWM signal, and this is time, this is voltage. As you can see, this is 0 and this is more than 0, so we'll call that 1. That's logic level. So it's what it means is it's not using a very high voltage in order to be used. It also says its operating temperature, rated for fast switching, and fully avalanche rated. Over here we can see the package. It comes in Diode 220, and if we take a first look at the absolute maximum ratings. So what is the first thing we see? We see I drain, which is the current that comes in from here, and it's maximum rated for gate to source. So if I draw a MOSFET right here and gate, and here we have some PWM signal, and the peak is 10 volts, which is a 10 volt signal. We have the drain here, we have the source here. So that means if we take a multimeter or something and we measure this point, the gate and the source, we measure this at 10 volts. So it doesn't matter if this is 20 volts or this is 10 volts. but you have to be careful because we'll see that later. And this is for a temperature of 25 degrees Celsius. So if we approach higher temperatures, the current will drop the maximum current, which is obvious because it's heating up, and therefore you must use a lower current. The pulse drain current, which is the current that it's a current spike. For example, if we have a current over here and time, and we have a current and suddenly it spikes up, and this is for a small time, or well, let's make it even smaller, and usually it's mentioned somewhere. It's probably on the second page, as it has a marking over here for 1, and it's at 160 amps. So now we take a look at power dissipation, which says 110 watts. Therefore what it means is, for example, we have a current flowing in our circuit, and the voltage drop across this is a certain voltage, and the current through here has a certain value, and therefore the power dissipation is this current times that voltage drop, and apparently that shouldn't be higher than 110 watts, because then it will cause troubles. So next up is the linear derating factor, which is 0.71 watts per degree Celsius. What this means is the amount of power it can dissipate to its surroundings. Maybe we'll take a look at that later. And a very important piece of information, is the VGS, which is the maximum gate to source voltage. So as I said, if you put a multimeter right here, it will measure the VGS. So if I draw a circuit, and we'll come back to it later to discuss some of the issues with MOSFET. So for example, here we have 0 volts at the source, and here we have 15 volts, for example. Then this is always 0 volts because it's tied to ground, and this gate voltage should not be higher than this value, the 16 volts. So this is max 16 volts. And if you exceed it, for example 20 volts, there is a chance you will destroy the gate of this MOSFET, and therefore you will destroy the MOSFET. Okay, here's some parameters which are not that important to know for using them in your basic applications. So if you want to read about them, you can, and if you want me to tell you about it, I can make a separate video on it. but there's really no need to for now. Alright, the next is temperature, of course, which is the temperature it will operate best, as you can see also right here. That means it can get fairly hot and still operate pretty good. And so now we are going to take a look at thermal resistance, as you can see right here. First, what we see is junction to case. If you take a look at this picture, this is the case, the black part. So what does it say? It says 1.4 centigrade per watt, and let's assume this 110 watts. So we get T is that coefficient, or excuse me, which is 154. And if we look at this number and this number, or this maximum number, it doesn't really add up. But what we must not forget is the ambient temperature, which is usually room temperature. And let's say the junction temperature then is 20 plus the case temperature, which is 174 Celsius, which is the operating temperature before the case starts to get damaged. So that's how the case warms up. And then case to sink, which is heat sink. This is the temperature it gives off to the heat sink, which is typical. It says typical because it all depends on your heat sink as well. So it just says typical, there's no max, there's no min. And junction to ambient, which is, if we have the MOSFET over here, then the ambient temperature is right here. And this is the MOSFET radiating. So it's basically how the junction to ambient temperature rises per dissipated power in watts. But usually it doesn't really matter, because most of the time you'll look at these two. So now we are going to take a look at page 2. Well, first of all we are going to see the breakdown voltage of the drain to source, which is 55 volts as we saw. What does that mean? Well, if we have the MOSFET right here and we place a very imaginary barrier between the gate and the source, and it's very thin, and as we approach a potential difference, well, just a voltage, a potential difference that's higher than 55 volts, like it can be that the voltage just goes through the barrier, the imaginary barrier, and it leaves a broken pathway here, and that means you have a short circuit because they won't wait for the gate to charge up and let the electron flow. So basically you have a short circuit. You must not exceed that voltage, which is obvious. And here we have breakdown voltage temperature coefficient, which is not that important. I'm not going to talk about that really. But here's something important, which is RDS, which is basically if we have the MOSFET in its on state, therefore on state, we can see this as a resistor. Well, there's also parasitic inductance as well, stuff like that. But this is the RDS on. That means just here we have the drain, here's the source, and this is the resistance when it's on. So what it says is at various voltages and currents it will have a different resistance. And as you can see, if you apply a higher voltage to the gate, you will have a lower resistance. Therefore it's ideal to have a voltage that's approaching the maximum, but we'll take a look at it later at the graph, which shows ideal gate source voltages, and you see it is lower. Therefore, if you take a look at the equation for power dissipation for resistance, which is V times I, and due to Ohm's law, V is IR, therefore this whole becomes I squared R. As you can see, we have I in squared and we have the R. So if it gets lower, there is less heat and the current can increase, therefore you can have more current flow, which is ideally what we want usually. So next up is VGS threshold, which is the gate threshold voltage. As you can see, it's suitable for logic levels, which are around 5 volts, usually 3.3 volts, 12 volts. Those are usually logic, and what the threshold voltage is the conductance. For example, if we take a look at RDS, and this is the voltage from gate to source. Let's assume this is almost infinite, and therefore if we have 0 volts here and we reach a minimum voltage of 1, so this is 1 volt, it drops to a point, and this 1 volt varies between 1 and 2 volts. So then we get a sort of linear decay, where it becomes more and more conductive. So yeah, you basically want to be in this region, and you must take a look at the data sheet for that. And experimentation is also a very good method. And what's next is the gate trans conductance, which is not really important. It's basically a parameter for which has to do with the gate width and the internal chemistry, and it's not really important to know for switching. Well, drain to source leakage current speaks for itself. Is just the current that gets lost in the internals. And same here. Forward leakage, reverse leakage, gate to source, which is just this connection over here, which is usually isolated. This, there still is a current that is leaking, and that's these values. So you never get a perfect isolation between the two. So next up is a pretty important part, which is the total gate charge. And as I said before, there are a little bit of capacitance right here. Well, I can just draw it like that. This is some capacitance, and this total gate charge is the charge that is being held at the gate. It doesn't make sense yet, but it's very important, especially in high frequencies. What this means, there is a little bit of, well, I can better explain it with an analogy. Let me zoom out a bit. Mechanical analogy. Let's say we have a switch right here, and we have a lever that controls the water that's flowing. It's flowing in this pipe, let's say. So here we have a bucket which can hold a gate charge, and therefore it must be charged. And if this bucket, let's say we have a current water that fills up this bucket, and let's say we have a very fast gravity, this means this bucket will be filled and it will tip the lever, and the current from drain to source can flow. So first what must be done is fill this bucket. We must first fill the bucket with water, and in this case we fill it with electrical energy. So I hope that analogy was a little bit clear. If not, we'll see about later, perhaps. So when the that's a really important part in high frequency and gate driving, because you have to supply a certain current, which is, if I remember correctly, is Q over T. This is usually D, and then you simply integrate Q over dt, and you get a Q over T. And if we look at here, we have a 48 nanocoulombs, and let's say we want a very high switching speed, let's say 20 nanoseconds. The nanos cancel out, and we have 48 divided by 20, which is 2.4 amps. Therefore, we must deliver 2.4 amps to the MOSFET gate somehow. 2.4 amps is a lot, and 20 nanoseconds is also very little. As you can see, it doesn't even turn on that fast. Or it does actually turn on, but it doesn't rise as fast. Which is a part for later, but let's first look at the next value, which is the gate to source charge, which is this charge over here, this capacitance. And this is basically a part of this capacitor circuit. And over here we have the Miller charge, which we will see common. Basically, it has to do with this region of turning the MOSFET on. This is the Miller region, and this is where the charge has to be charged, to simply say it. And it's not a small charge, as you can see. And what this can do is it can introduce switching losses to your circuit, because there is this little period where it does nothing. It's basically charging. And you must keep that in mind with zero voltage switching, ZVS, zero current switching and such. So I found a pretty good experimental result of the Miller charge. As you can see, it's right here in this region, and you can see, if I didn't make this, but it can overlap with this and this. And if one is current, for example, we have, this is the, I think it's the drain to source, or the gate, and this is the gate, and here we have complete turn on. You have this part over here where it's not fully on, but it starts conducting anyway. So what you will have is, if I can draw it like that, and we have the current going or we have the with drain to source going like this. So what we have, VG, V drain to source, and basically we have a overlap. What's problematic with this overlap is that we also have a current that starts to rise when the it's a more sharper rise over here. And even more important is this drain to source and this drain to source current. As you can see right here, we have this overlap, which is V times I power, and this is called switching losses. Therefore you must find a way to overcome it. And that's a part of that's making, we will talk about that later in the topology. So that's a very important thing to realize, that there's charge everywhere. It's mostly not wanted, but it's there. So the turn-on delay, which kind of speaks for itself, it's the delay for it to turn on. Therefore we have a little bit of delay before the signal says it to turn on, and it actually turns on. And then we have the rise time. Let's say, right here, this little region is the rise time. So this is not a representative square wave, because there is no rise time. But if you zoom in to this section, you get this. That's the rise time. It's an art to get it as low as possible. As you saw in my video, I had 25 nanoseconds for my switching circuit, and I didn't even measure the drain to source, but this is the drain to source, rise time. You also have the gate rise time, which is depending on this formula, and this is then as low as possible because this is the rise time. So turn off delay, same thing as turn on delay. Fall time, same as rise time, but then for falling. Internal drain inductance, which is parasitic inductance. It's basically another voltage drop. For what you have to keep in mind. Let me make these inductors, and maybe make this inductor as well. And the circuit for the voltage drop across an inductor is the inductance times dy dt. Therefore, this little part over here, which is depending on the frequency you're switching with, and the current, the drain to source current. So you must beware of not going too high, because you will have voltage drops, and again V times I, this will have even more losses. So as you can see, it's in the nanohenries, but still it's there, you can't get rid of it. So now for the capacitance, as we talked about earlier. Here we have CISS, which is the input capacitance, which is gate to source, and gate to drain, which is these two, which is basically the entire capacitance on the gate side. We have the output capacitance, which is COSS, which is drain to source, and gate drain, which is these two. And we have CRSS, which is reverse transfer capacitance, which is only gate to drain, which is this over here. It's an important feature. For example, in zero voltage switching, it's pretty good to have this. I mean active phase shifting, for example, and we will talk about that later. It's a part of my charger for my railgun project. It's going to be very high power, and high power needs high efficiency and such, so it's pretty important. So next up is the diode characteristics parameters, and that's basically this diode that's going from source to drain, which can create a circuit like this. And if you take a look at it, assume we have a current flowing from here, which is source to drain. Let's say it's flyback voltage from a motor or transformer, and the maximum it can continuously conduct is 47 amps pulsed. And again, you have to look at node 1, as we saw before, and now we can see it. It says, take a look at figure 11, but it's actually just 160 amps, and then we actually have to look at the figure to see what under what conditions, but that's not needed. And VSD, which is the diode forward voltage, as you know probably already, hopefully, is that there must be a minimum voltage for the diode to conduct in this direction, and that's only if the voltage is equal or voltage is greater than the forward voltage, so it's unequal or greater than. But what you also know is forward voltage is always there, and it's there as a voltage drop across the diode. And what you must be careful of is, again, power losses. In this case, this will be 1.3 volts, and this, let's say, maximum of 47 amps, which is, if I calculate, 61 watts, which is a lot. And then we have recovery time, reverse recovery, which is basically how fast it can recover from conducting, and reverse recovery charge, which is the parasitic charge that's holding by the diode. And it's simply the same. It's first being charged a little bit before it starts to conduct. And we have the forward turn on time. Turn on time is negligible, which is dominated by Ls plus Ld, which is the internal drain and source inductance. And that's basically because you hopefully know what inductance does. If not, let's make a graph of the current through an inductor. And let's say we have a square wave of just this. Then we have a current that has to build up first as a magnetic field and such. And as you can see, it's basically the integral of voltage. So that was the end of part 1 because this is not all that there is to MOSFETs, and we're going to talk a lot more about the properties and characteristics, parameters and such, but I think this is enough for now, and we'll continue later. Thanks for watching. If you have any questions, you can leave them in the comments, and I will try to answer them. Perhaps I cannot answer all due to my own lack of knowledge, but I think I can answer them all. Thanks for watching.